We will now continue with our study of electric field due to extended charged objects. And this time we will discuss Gauss's law to make it easy for that study. Now, first of all, let's review an important concept that we discussed when we started discussing electric field. Now, do you remember the concept of electric flux that we discussed? What is flux? Well, definition of electric field using electric flux phi. Do you remember the definition of electric field using the concept of electric flux? We said electric field is flux per unit area. Well, we're going to use that. Electric field is normal flux per unit area. Normal is at right angles. Is that right? Yes. So E, the electric field, is phi divided by the area flux per unit area. That means the total flux phi crossing a given area A will be phi equal to E times A. We will use both these concepts in developing Gauss's law. If the electric field lines makes an angle theta with the surface A, remember only the component of the electric field at right angles to the surface will contribute for flux. So if the field makes an angle with the surface, then the component of the field at right angles to the surface will be EA cos theta. When theta is 0, cos 0 is 1, phi will be equal to EA. Now we will be considering all cases where the theta is 0 or the field lines will be at right angles to the surface all the time. Alright? Okay. If a surface contains more positive charges than negative, there will be a net flux leaving the surface. Now, do you remember we talked about the concept of field lines? We said the number of lines of force or the number of field lines either converging or diverging from a charge is proportional to the quantity of charge that is contained there. So, can you connect those two and understand this? If a surface contains more positive charge than negative, there will be a net flux leaving the surface. Suppose this contains some electric charge, and if there is a net flux leaving the surface, that means the amount of positive charge contained in here will be greater. You see, if the flux due to a positive charge will be directed away from it, and the flux due to a negative charge will be directed towards it. Now, if the surface contains negative charge, the flux will all be directed towards it. If the surface contains positive charge, the flux will be all diverging from it. Now, if a surface contains more positive charge than negative charge, it means the surface contains a net positive charge. There will be a net flux leaving that surface. Similarly, if a surface contains more negative charge than positive, there will be a net flux entering the surface. I hope you understand the distinction between the two. If a surface contains no net negative charge, now suppose this surface contains equal quantities of positive and negative charge. That means if a line of force, if a field lines come out of the surface, then one must go in. That means the net lines coming out will be equal to the number of lines going in. That means there is no net charge. So if a surface contains no net charge, the net flux leaving or entering will also be 0. I want you to understand these statements very well, because Gauss's law is going to use these statements. What it means is that if this surface contains more positive charge than negative, then there will be a net flux leaving that surface. If this surface contains more negative charge than positive, then there will be a net flux entering that surface. You understand the meaning of flux? It's the number of lines of force that will be either entering or leaving. If a surface contains no net charge, then the number of field lines leaving will be equal to the number of field lines entering. In other words, there will be no net flux. Or you can say the net flux leaving or entering a surface is a measure of the net charge contained in that surface. In other words, the net charge inside is 0. You can see there's a positive charge and a negative charge. There are 4 field lines leaving. There are 4 field lines entering. The number of lines of force leaving the positive charge is equal to the number of lines entering the negative. The net charge is 0 inside. The net flux either entering or leaving also is 0. Alright? On the other hand, look at this. This surface contains a net positive charge. That means there will be a net flux leaving the surface. Consider a positive charge Q placed inside a spherical surface of radius r. This is a spherical surface, and there is a charge Q placed on it. The radius of that surface is r. Now, this is very similar to my basketball. I have a spherical surface of radius r, and I have placed a charge Q on it. Now, tell me, what is the electric field at a point on the surface of the field? Now, the charge that you give to a spherical surface like this will act as though that charge is at the center of the spherical conductor. So consider a positive charge Q placed inside a spherical surface. The charge Q is placed inside the spherical surface. That means any point on the spherical surface is at a distance r from that charge. Is that right? Where r is the radius. That means the electric field at any point on the surface will be kq over r squared, where r is the distance of the point from the charge. The charge is at the center of the sphere. I hope it is clear that the electric field at a point is kq over r squared. The electric field at any point on the surface, on the spherical surface, will be at right angles. Why is the electric field at right angles? Because when you have an electric charge at the center, the field lines will be along the radius. And if you draw any radius, that radius will be always at right angles to the surface of the sphere. That means the field lines will all be coming out of the sphere at right angles. Can you imagine all those thousands of field lines coming up at right angles to the surface? The electric field at any point on the surface will be at right angles to that surface at any point. Alright? And that electric field will be given by this expression En. What does E sub n stand for? The normal electric field. Normal means at right angles. the electric field at right angles to the surface of the spherical surface is kq over r squared. The net flux leaving the spherical surface. What is the net flux leaving the spherical surface? The total flux leaving the spherical surface will be the electric field, which is the flux per unit area. If you multiply this with the total area of the sphere, what is the area of a sphere? We just talked about it. What is the surface area of this sphere? It is 4 pi r squared. So, if this is the electric field, remember electric field is flux per unit area. If you multiply the electric field with the surface area, that will give you the net flux leaving the spherical surface. Let's write down that. Phi net equal to the electric field multiplied by the area, and that will be kq over r squared is the electric field, and multiply that with the area. What is the area equal to? Well, the area of a spherical surface is A equal to 4 pi r squared. Here, this r equal to this big R. That is the radius of the spherical surface. Therefore, phi net equal to E is kq over r squared times A is 4 pi r squared. So, the net flux leaving the spherical surface that contains a charge q is given by this quantity. And you notice r squared will cancel, and what does it give you? It gives you 4 pi k times q. What does the q stand for? Q is the amount of charge inside that surface. So, let me say that again. The net flux leaving a surface is 4 pi k times the charge inside that surface. And if you now write this k, remember our k can also be written as k equal to 1 over 4 pi epsilon naught. If you now replace this k by that value, what will be net flux equal to? Phi net equal to q over epsilon naught. Well, you see, these two statements summarizes the law that we are looking for. What is the law that we are looking at? Well, if Q inside is the net amount of charge within a surface, then the net flux leaving or entering the surface is given by phi net is 4 pi k times the charge inside, which is the same as Q inside divided by epsilon naught. These are the same two equations we developed in the last lesson. And this is the statement of Gauss's law. So what does Gauss's law say? Gauss's law says, if a surface contains a certain amount of charge, then the net flux either leaving, if the charge is negative, the flux will be leaving. If the charge is positive, I'm sorry, I didn't say it correctly. If the net charge inside is positive, the flux will be leaving the surface. If the net charge is negative, the flux will be entering the surface. So the net flux either leaving a surface or entering a surface will be given by 4 pi k times the amount of charge inside that surface, which is the same as, if you replace the k by 1 over 4 pi epsilon naught, it will become q inside divided by epsilon naught. And this is the statement of Gauss's law, where the value of epsilon naught is 8.8